Good evening. I'd want to welcome all of you back, some of you back to one of our campuses, and some of you new faces, some of them we've seen many times. So we're really excited to have you. We also have a bunch of people who are joining us virtually. So I'm Eric Isaacs. I'm president of the Carnegie Institution for Science. And Mike Walter is going to introduce our speaker tonight, Bob Hazen. But I just wanted to make a few comments first, which is, being here at Carnegie is one of the great privileges anywhere to do science here. For me in particular, it's that I get to get up in the morning and talk to great scientists who do an amazing range of things. Now, what makes us, everyone does, a lot of places doing science. What makes it a little special here is that our scientists have a little more, maybe a lot more latitude to get up in the morning and decide for themselves what to think about. And as a result, you will find, or you'll see tonight, we're very privileged to hear this talk tonight, you'll find that people here think more boldly in some ways, right? And think about things in different ways that you wouldn't think about in the past. And we're privileged enough to hear that tonight, which is, we think of minerals, we think of rocks. I'm a condensed matter physicist. I think of rocks all the time. I study them with X-rays and magnetic fields, et cetera. But you can go pick up rocks outside. But what you'll hear tonight from Bob Hazen is a whole bigger way to think about these minerals and how these minerals have certainly evolved. He's thinking about it in the context of evolution. We think of humans and we think of biology as evolving, but he's thought about minerals and how they evolve, how they co-evolve with living things on Earth. But a really interesting perspective on these materials, these gorgeous materials here, which at first glance are gorgeous, and you want to hold them, you want to have them in your house, you want to have them on your finger, you want to explore them. But what Bob has done, because of the way he's able to think when he comes into work, is that he's able to think of it in a bigger context. And so we're going to hear in a very interesting way how Bob is now thinking about how the Earth's minerals and exoplanets have evolved over the many millions and millions of years here on Earth. So I'm sure you'll enjoy it. But I'm now going to ask Mike Walter, who's the director here of the Earth and Planets Laboratory, to give an introduction for Bob so you can get a sense of his accomplishment.
I have my pleasure. Thank you, Eric, and welcome everyone. It's really a great pleasure for me to introduce tonight's speaker, Carnegie mineralogist, astrobiologist, popular science author, Robert Hazen, Bob. Bob's engaged in, as Eric was describing, an incredibly bold and creative career here at Carnegie Science for coming on to a half a century. Sounds scary, Bob. In 1976, Bob was appointed as a research associate, and just 2 years later was named as a staff scientist here at Carnegie at the Geophysical Laboratory at the time. During his years at Carnegie, Bob earned global renown as a mineralogist and played a key role in establishing two fields. One of those is high pressure mineral physics, and another one is astrobiology. Bob is also the Clarence Robinson Professor Emeritus at George Mason University, and he taught there for many years and impacted the lives of countless students along the way. It's fair to say that Bob's unique insights and ideas, as Eric was describing, have fundamentally changed the conventional wisdom and dogma around mineralogy, such that it's taught differently now than it was even just maybe a decade ago or so. Over the past decade, Bob has pioneered the concept of mineral evolution, linking an explosion in mineral diversity to the rise of life on Earth and the resulting oxygen-rich atmosphere. Bob also introduced the idea of mineral ecology, which analyzes the spatial distribution of minerals on Earth and predicts which ones remain undiscovered and define our planet's mineralogical distinctiveness, especially when you compare it to other planets. And each of these have their own mineralogical distinctiveness, which says something about how they evolved. Bob has most recently been applying sophisticated computational data analytic approaches and visualization tools to probe geological databases, large databases of minerals and rocks, revealing new information about their mineral diversity, things like protein evolution, mass extinction events, and much more. Bob's extraordinary career has earned him many accolades, too many to recount here. Most notably, he was just this year the 2022 recipient of the International Mineralogical Association Medal of Excellence. So congratulations, Bob. He's a fellow of the American Association for the Advancement of Science and the American Geophysical Union. Bob is also featured on dozens of radio and television programs, has authored or co-authored more than 25 books, including most recently the popular science book, Symphony in C, Carbon and the Evolution of Almost Everything. Tonight, Bob will share how something as fundamental as a mineral can hold hidden secrets of Earth's 4.5 billion year history. So please join me in welcoming Bob Hazen.
Thank you, Mike. Thank you, Eric. The opportunity to be at Carnegie as a scientist for almost half a century has been an unbelievable privilege. I wake up every day feeling lucky, looking forward to being in the laboratory and studying minerals, because minerals are fundamentally important. They're the raw materials for technology. They're essential to agriculture. In fact, every living thing depends on minerals. Minerals are the key to understanding planetary history, the evolution of planets, and that includes biological evolution. Minerals are absolutely fundamental in the foundation of solid-state chemistry and physics. Mendeleev's discovery of the periodic table, Bragg's discovery of X-ray diffraction, the chemical bond, the nature of materials at extreme pressures. These are all parts of mineralogy. And of course, as you've already seen, minerals are just astonishingly, jaw-droppingly beautiful natural objects. They're the oldest things you can hold in your hand. Some of them are more than 4 billion years old. They tell the stories of the origin and evolution of life on Earth. And every mineral is a time capsule. It's just waiting to be opened to tell its story. And I love those stories. So what I want to do tonight is to look at 3 intertwined questions related to minerals and evolution. And the first is just this basic idea: how has Earth's mineralogy changed through billions of years? What's the best way to classify minerals in order to highlight those evolutionary changes? And then, stepping back to a rather large question, is there a missing law of nature that relates to evolution? Okay, so this story for me began in 2008 when a group of colleagues at the lab and elsewhere published a paper called Mineral Evolution. It was a story of the change of minerals through Earth history. And basically, this is the key point, that mineral evolution is the study of the changing diversity and distribution of minerals as a consequence of new physical, chemical, and ultimately biological processes. Now, I should tell you the definition of a mineral species, and this is kind of a term of art. It may sound a little strange to talk about species and minerals in the same sentence, but the International Mineralogical Association, IMA, says that it's a naturally occurring solid. It has an idealized chemical composition based on the major elements. So quartz is SiO2. And it has an idealized structure. And every unique combination of a chemical composition and a structure is a species. As of right now, we're approaching 6,000 approved species by the IMA. Okay, mineral evolution then looks at the change in mineral species over 4.5 billion years of Earth history. And that includes the diversity of those species. It includes their distribution across the surface of Earth. It includes the compositional ranges, and that includes trace and minor elements that reveal much about how they form, and even things like the sizes and shapes of the minerals, things not included in the IMA system. Now, we think about near surface processes, the upper 3 kilometers, and that's because that's what we can study. That's accessible to us, and it's what's going to be accessible on other planets and moons as well. And also, it's where you have direct interaction with biology, and it turns out that's really important for minerals. Okay, I have to take a little aside here and defend the use of the word evolution. Over the years, we've had many people, mostly biologists, who have said, well, minerals, you can't talk about evolution and minerals in the same sentence, where this is a biological thing, it's not a mineralogical thing. And I disagree. 100 years ago, Carnegie staff scientist Norman Bowen published The Evolution of the Igneous Rocks, and we're really just following in his footsteps. This means change through time. It means something more. It means complexification. And in evolving systems that I'm talking about, you do see an increase in diversity and patterning and what we might just call the complexity of the system. Oops, it doesn't mean this. It's not Darwinian evolution, so you can erase that from your mind. But it is an evolving system. And here's this idea that new minerals formed by a combination of physical, chemical, and ultimately biological processes. And what we did in that first paper was say there are 10 stages of mineral evolution spanning Earth history. And so let me take you through those stages to give you a sense of this qualitative narrative of Earth history and its minerals. Now, even before Earth formed, there were about 20 minerals that formed in the atmospheres of very old stars. And as those atmospheres expanded and cooled, they were rich in elements like carbon and silicon, oxygen, nitrogen, and so you formed some very high temperature phases. We call these the minerals. They formed from about a dozen different chemical elements that were abundant in the atmospheres of stars. And you might say that the question of mineral evolution boils down to how do you get from 20 minerals with a dozen essential elements, where we started, to what we have today, which is over 5,800 approved minerals with 72 different essential elements. That's the mineral evolution story. Stage one, these are the earliest condensates in the solar nebula, about 90 different minerals that are preserved today in what are called chondrite meteorites. And then those chondrites came together, they formed larger and larger planetesimals. When you got to 50 or 100 kilometers in diameter, the internal heat caused them to melt. You had a metallic core, you had a silicate mantle, you had aqueous alteration, you had thermal alteration, you had impact alteration, giving you about 300 different minerals altogether. Those are the minerals that still fall to Earth as meteorites and every other terrestrial body. And you can think of this as the starting point of mineralogy in our solar system. Now, this is probably the end point of dry worlds like the moon or Mercury. We don't think that there are many more than 300 mineral phases in those bodies. If you have a wet world like early Earth, you can also form clays and hydroxides and other sorts of hydrated minerals. That gets up to maybe 450. And we think this is probably the end point of Mars, stage 3. But Earth is much larger. It has other tricks up her sleeve. You can partially melt the first rocks, which are basalt, the same kind of rock that's pouring out of the volcano in Hawaii right now. And when you partially melt basalt, you create granite. You also select and concentrate some rare elements and form lots of other minerals, about 1,000 in all, in what are called pegmatites. This gets us up to stage 4. Stage 5 is even larger fluid rock circulation. The crust, the upper mantle, basically hundreds of millions of cubic kilometers of Earth's crust is reprocessed, and you get new modes of volcanism, giving you new minerals. You get new massive base metal deposits with hundreds of new minerals called sulfides and sulfosalts. You have mountain building, and in the cores of mountains, you create new minerals which come to the surface through erosion, and you have this new kind of high pressure suites, roughly 3,000 minerals in all at this point. And here we've now had 3,000 species formed purely through chemical and physical processes. But remember, I told you that we now have over 5,800 approved species. Where do they come from? I think you've anticipated the answer. The answer is life. Life is an incredible generator of new minerals. And to me, this is fascinating. For a time in my career, I was studying the origin of life. And we used minerals in those studies because minerals are catalysts, the reactants. They act as templates for organic reactions. They protect the molecules on surfaces while they are scaffolds for building larger and larger molecular structures. And so here we have this fascinating dichotomy of minerals being essential in the origin of life, but then life being essential in the origin of minerals and the co-evolving geosphere and biosphere. So we move ahead. Stage 6 is the earliest period of life on Earth where microbes use the chemical energy of rocks at Earth's surface to survive. They didn't produce a lot of new minerals, but they redistributed those minerals. And then the great punctuation event, stage 7, that's the photosynthesis, producing oxygen in the atmosphere. Earth's surface essentially rusted, but not just with iron, with many, many different elements. More than 2/3 of all the known copper minerals formed after this period, and all those beautiful blue and green phases, those are oxidized minerals of copper. Uranium, almost 90% of all the known uranium minerals formed because of reactions with oxygen in the atmosphere. and hundreds of other phases, just beautiful minerals of all sorts of what are called redox sensitive elements. Those minerals formed after the great oxidation event. Stage 8 is a long period, about 1 billion years, when the oxygen in the atmosphere started penetrating the oceans. First, the upper layers were oxygenated, then deeper and deeper and deeper. It took about 1 billion years for this to happen. I consider this a kind of great titration event, if you will, when the iron in the oceans were removed and settled down as iron oxides on the ocean floor. Not a whole lot of new minerals, we don't think, but still a huge change. After this period, about a 300 million year period when there was cycles between global glaciation and global tropical climates, where during some periods, the most abundant mineral on Earth was ice, H2O in the ice crystal structure. And other periods of time, Earth was so hot that ice may have gone completely extinct, only to come back again. And finally, stage 10, this is the biomineralization of the Phanerozoic. At the last 500 million years or so, life enters land. You have whole new kinds of mineral forming environments. Root systems formed clays. You have coal measures. You have taphonomy of cacti as they die. You have bird poop, which forms dozens of new minerals. And you have, of course, carbonate and phosphate and silicate forming bones and teeth and shells. Amazing. I've got to tell you one story. This is one of my favorite stories about biomineralization. Trilobite eyes, look at all those facets. Every one of those facets is a single crystal of the mineral calcite. Now, calcite's got what's called a C-axis, and that eye is pointing right out at you. Every one of those lenses is a single crystal of this mineral calcite. Great, but calcite makes a terrible lens because red light and blue light bend differently. It's called chromatic aberration. So calcite makes a lousy lens. But life figured out a way through evolution to fix that. Because if you change the calcium carbonate of calcite, slightly adding a little bit of magnesium, you change the way light bends. And if you have a circular eye and you have a higher concentration of magnesium in the middle, and radially it becomes less and less. So the ratio of magnesium to calcium changes. You can correct for chromatic aberration. Now, if you were an engineer and had to design a calcite eye like that, it would be a horrible problem. But life finds a way through natural selection. You select for what works. And we'll come back to that theme later on. Okay, so what have we learned from this? Near surface mineralogy has changed dramatically over 4.5 billion years. We see that the evolution is characterized by a whole series of new mineral forming processes, and that life played a really critical role. Also, this turned out to become a very important way of framing in education and engagement about minerals and the public. I have to take you back many, many years. When I was a 10-year-old child, my family moved to the New York City area, and I would go into the American Museum of Natural History on a regular basis because I would just, the dinosaurs were great and other exhibits were great, but I just loved the minerals. And they were arranged in the Morgan Hall of Gem and Minerals by what was called the Dana system. That's the system where you have chemistry and you have structure, the same system we use to classify by the IMA. And I went and I memorized the names of minerals and their formulas, and I just loved it. This is the American Museum of Natural History, the new exhibit of minerals that opened last year. And it's organized around mineral evolution. Now imagine how I feel being a 10-year-old boy seeing those specimens, now seeing the same specimens that I remember as a child, and they're arranged in this new way. A way that I think is much more powerful because it tells a story, and every mineral fits a role in a very dramatic 4.5 million years drama. And it isn't only the American Museum, the Vienna Museum, the Paris Museum, the Edinburgh Museum, the Houston Museum, many museums. My favorite just this year, the new Tucson Gem and Mineral Museum. And you walk there, it's a hall of mineral evolution. So this has become a powerful way to train people, to teach them and engage them in mineralogy. However, I hope you all realize that what I've told you so far is a very qualitative story. There's not a lot of mathematical rigor or exact dates assigned to any of this at this point. And what we need is a much more quantitative approach. So the next thing we did, starting in 2009 and for about a decade, is we built the Mineral Evolution Database. And this was in conjunction with our colleagues at the University of Arizona, Bob Downs, who is the professor of mineralogy. And this rough database, which contains all the IMA-approved minerals, you can search by composition, you can search by structure, other things. Well, we built the Mineral Evolution Database, which now has 200,000 mineral locality age data. This was done by hand, led by 2 graduate students, Josh Golden and Alec Pyers, but also an army of undergraduates at Arizona, line by line, going through papers, adding data. And this allows us to do all sorts of things we couldn't do before. For example, we can plot for all the known manganese minerals where we have ages. That's what we see here. On the vertical scale is the number of mineral locality pairs. On the horizontal scale, we have ages going back to 4 billion years. And you see 2 things in this diagram of the distribution of manganese minerals through time. They're colored by their oxidation state. So as you see the increasing amount of purple, that's the more oxidized manganese minerals, the result of oxygenation of the atmosphere. But you also see pulses of mineralization. And that's the result of the supercontinent cycle. And we can actually visualize this using our colleagues from the University of Sydney in Australia, who have designed the G-Plates platform. This is a way you can go back as much as 1 billion years and see how Earth's surface looked. And the continents have moved all over the place. It's just dramatic. Here's the diagram now. You're going to be seeing dots that represent manganese minerals, when they formed, their oxidation state, and where they formed in the context of the ancient Earth. So we're going to start in this case about 360 million years ago. You see the continents moving. And what you're going to see now is the formation of the supercontinent called Pangaea. And as you see those dots appearing, most of them are occurring along plate boundaries, where mountains are built, where plates collide, where subduction is happening, and mineralization occurs near those plate boundaries. It's really, there's Pangaea. Now we're going to see 195. We're going to start seeing Pangaea breaking up. There's the Atlantic Ocean just beginning to form. The South Atlantic is still tied as Africa and South America are here. So you can see we can learn a huge amount of how mineralization occurs, where it occurs, when it occurs, using the Mineral Evolution Database. So we see this episodicity corresponding with the supercontinent cycle. We see changes due to oxygenation of the atmosphere and other redox changes. But the thing is, this Mineral Evolution Database does not exploit the full power of mineral data. And so I want to ask this question: what's the best way to classify minerals to reveal Earth's evolutionary history? And the answer will lie in mineral informatics, because minerals are incredibly information rich. They contain so much information: trace and minor elements, dozens, scores of different elements, isotopes, structural defects, solid and fluid inclusions. They're all the different kinds of morphological characteristics, the physical and optical, electronic, magnetic properties, petrologic context, all this and more. And so we need databases. We rely very much on the rough database that I told you about. Also MinDat, an amazing data resource run by Jolly and Ralph in London. It contains more than 1 million mineral locality data and much, much more, but also all the publications, the Handbook of Mineralogy, the multi-volume set, Rock Forming Minerals by Deerhowy and Zussman, and literally tens of thousands of papers in the literature. And using these resources, we can classify minerals in a different way. Now, think about it. What is the point of having a classification system in science anyway? Well, the first thing is so you can describe one mineral, and I know what you're talking about when you talk about diamond or quartz or calcite. We can speak to each other and know that we've got a baseline there. But another reason for having a scientific classification system is because the classification system can advance a theory. It can help you build new ideas and new concepts. And so in this way, you can have more than one valid classification system at the same time. That's why we're proposing a different classification system. Remember, what IMA says is a mineral has an idealized composition and idealized crystal structure, which means they're using the minimum possible bits of information. And we're going to say, let's use the maximum amount of information. If we want to understand the coevolution of Earth and life, The only way we can do that is a new classification system that incorporates deep time. Think about Earth, how it's changed. Early Earth was a black, scarred, volcanic world, but it's gone through these phases and these changes. And an evolutionary system of mineral classification has the potential to inform theories of how the planet changed. So we can ask major questions. We can say, how does life emerge? How does life evolve? It's even possible that we can ask, is there life on other planets using minerals? Okay, so the primary tangible evidence we have are these minerals. They're time capsules. And so we've begun the evolutionary system. This is work I've done with my collaborator, Shauna Morrison. We've now published the first 6 parts of the series. Part 7 is in press. Part 8 we're working on. There may be 4 or 5 parts after that. It's a huge, huge project. And what we did is we changed the IMA system a little bit. We say some species are split into several natural kinds. Some are lumped into single natural kind. And we also add some non-crystal materials that are not considered by IMA. Let me show you what I mean. So diamond is defined by IMA as pure carbon in the idealized diamond crystal structure, which, by the way, you can describe in about 7 or 8 bits of information. But here's presolar diamond. That's a diamond that formed around a star many billions of years, perhaps billions of years before our own solar system. It's microscopic, it's a nanoscale. That's different from a type 1 diamond, which formed deep in the earth, in the mantle, high temperature, high pressure, in an aqueous solution saturated in carbon. Different than type 2 diamond, which formed at high temperature and high pressure in the mantle, but in this case, a metallic melt saturated in carbon. That's different from impact diamond. It's different from carbonado, which nobody really knows what it is. And so there's at least 5 different kinds of diamond here. Okay, think about apatite. It occurs as tiny little grains in meteorites, in big, beautiful crystals and pegmatites, but it also is in your teeth and your bones. Now, according to IMA, these are all calcium phosphate. They're all apatite. But we would say they're very different kinds of apatite. The world record, pyrite, we've identified 21 different kinds of pyrite. Some formed at high temperature, some at low, some in an aqueous environment, some in a sulfide-rich fluid. Some of them are abiotic, but others are formed by microbes. I would say if you found pyrite on Mars, your first question should be, great, what kind of pyrite? And that's what our classification system does. Now, in other cases, we lump minerals together. These are tourmalines. They're beautifully colored. They have compositional zoning so that in one crystal like this, because of different ratios of magnesium to iron to aluminum to fluorine and other elements, you can have as many as 7 different IMA species in a single crystal. We think it's one kind, so we lump them together. And finally, we include volcanic glass, really important, not part of IMA. We include coal, tells you an awful lot about Earth history, not part of IMA. We include other things that are amorphous, but extremely common in Earth's surface. And this is important. In Mars, Shauna Morris and I are on the Mars ChemMin team, an X-ray diffractometer. And there's some materials you just can't get X-ray diffraction off of. In some cases, 50%, in some cases, as much as 70% of the soil on Mars is amorphous. How in the world are we going to understand Mars and its history if we ignore that 70% and say, well, it's not a mineral, so let's not think of it. It's got to be part of your classification system if you're interested in the evolution of worlds. Okay, so what we did, especially during the COVID lockdown, is put together 2 papers, one on the paragenetic modes, that's how minerals form, and the other on lumping and splitting, which I've just told you about. And the idea here, this was a labor of love, 6 months, COVID isolation. Margie will remember sitting there hour after hour after hour, day after day for 6 months, 5,700 lines, each representing a different IMA approved mineral, 60 columns, each representing a different way that minerals formed. And if you look at this chart, you'll see that each mineral has 1 or more ways that it forms. There are about 10,500 boxes checked. That represents 10,500 different kinds of minerals in those 5,700. And this allows us to do a huge amount, allows us to make an evolutionary system. We used a binomial nomenclature, just like Linnaeus did. The second word is always an IMA species or something close to it, like graphite, form of carbon. The first tells you what the environment is, type 2 supernova. Or there's moissanite, that's silicon carbide, formed in an AGB star. And then we can plot this on what's called a bipartite network diagram. Our colleague Anirudh Prabhu is the designer and the mastermind of these networks. And what you're seeing here are two kinds of nodes. The star-shaped nodes represent different kinds of stars. The diamond-shaped nodes represent different kinds of minerals. Every mineral is linked to one or more star. Every star is linked to one or more minerals. This is the minerals that I told you about. Part 2, we get to the solar nebula and interstellar space. You start expanding the network by the earliest condensates from the solar nebula, and also some of those dense molecular cloud phases, the things that occur as ices. So that's part 2. Part 3, we look at the primary chondrule minerals. Think of those as the first igneous droplets in the hot, cooling solar nebula. About 100 minerals altogether. Expand this to include planetesimals, impact minerals, minerals altered by heat, minerals altered by water, about 300 minerals. These are all the minerals that are found in meteorites today. They still fall on Earth. It's the same phase 2 or part 2 that I told you about earlier. And then we expand this to our estimates of what might have been the earliest Earth crust. None of that survives, so this is a speculation. But we see an expanded network. In green are Earth minerals, in red, meteorite minerals, in yellow, those that occur, we think, in both. There's that original part 1 network. That's the stellar network, still embedded there. It has to be. But we're just building and building and building. We think this is probably similar to the mineralogy of Mars, 450 minerals. And now we're going to fast forward to the end. Here's all 5,700 minerals. This is the first diagram ever of all of mineralogy. And what you see is 5,700 brown nodes connected to about 60 different modes of formation, colored by various means. The green are biological minerals, for example. And we've learned a huge amount by studying a network. There's so much information embedded in this. For example, more than 90%, we think, of all minerals on Earth formed directly or indirectly by water-rock interactions. Water plays a huge role in the diversification of the minerals in a planet. If you don't have an active hydrological system, you're not going to have a lot of minerals. Our second discovery, and this to me is just astonishing. There are 41 rare mineral forming elements, 41 that represent 1/100th of 1% of Earth's crust. 1 in every 10,000 crustal atoms. And yet those rare elements are essential in 42% of all the known minerals. So rare individual types of elements that are selected and concentrated by water, that's where water comes in here. You have local pockets where you have incredible mineral diversity as a result of that process. Earth does that. As far as we know, no other planet in our solar system does. And here's the idea about life. This just amazes me. Half of all minerals on Earth are formed through biological processes. More than 1/3 are only known to form through biological processes. What an incredible role life plays in the mineralogy of our planet. And so, Earth's mineralogy has evolved over 4.5 billion years as a consequence of new physical, chemical, biological processes. And we can develop this evolutionary system to exploit that fact. And now, please take a deep breath, because I'm going in another direction. And with some trepidation and some excitement, because I want to share with you something that's been developing over the last year or so. I want to ask if there's a missing law of nature that describes the behavior of evolving systems. Macroscopic physical laws. These are the ones that we experience in our everyday life. The laws of motion and gravity, laws of electricity and magnetism, the laws of energy, that is thermodynamics. Macroscopic because they pertain to the things you're being held in your chair by gravity. You're not falling to the center of the earth because of the forces of electromagnetism that keep you in your seat. they're macroscopic. They don't have to do with quantum effects, which we don't experience generally. They don't have to do with relativistic speeds near the speed of light or masses like black holes. So there are other laws out there, but the macroscopic laws are their own set. And all of these laws of nature have been used to describe our world, but are they sufficient to describe everything in the world? We have all these complex evolving systems, and we suggest that there is a missing law. That's a hypothesis I want to put to you tonight and see what you think of it. So for more than a year now, a group of us, 8 of us, have been meeting by Zoom, sometimes in person. We have Stuart Bartlett, a physicist from Caltech. We have Carol Cleland, Heather Demarest, and DJ Ahrens, who are philosophers of science from the University of Colorado Boulder. We have a group of Carnegie scientists, Jim Cleaves, Anirudh Prabhu, Mike Wong, astrobiology, origin of life, data science. And in particular, I want to point out Mike Wong, who many of you may remember just a few months ago gave just a stirring neighborhood lecture on the science of Star Trek. Mike's been the leader of the group. He's been organizing it, and a big shout out. It's been such a pleasure working with you on this exciting frontier. So what would a missing law of nature look like? First of all, it has to describe some universal trend in the macroscopic world. It has to be completely consistent with the laws of nature. It's not supernatural, it's part of the natural world. It's consistent with the other laws, but it doesn't follow inevitably from the other laws of nature. And that's key. So here are these 4 sets of laws, the macroscopic laws. And I want to go over them because I want to remind you what they are. And I want to point out that the discovery of each law first required the recognition of a conceptual equivalence in nature, something I call the principle of conceptual equivalence. So Isaac Newton, his great breakthrough in the laws of motion was that he realized suddenly there were 2 different kinds of motion in the natural world. No one else before him had said this. First, there's uniform motion. That includes both things sitting still and moving in a straight line at a constant velocity. And everything else is acceleration. Sort of love all these examples, but you can imagine that once Newton figured that out, he could say, changes in motion require a force. This was the definition of force, the first time. Force equals mass times acceleration, a specific equation, and that forces always act in pairs. Those are the 3 laws of motion. They apply to every motion that you experience in your everyday life. Now, Newton also came up with another great realization, a conceptual equivalence between an apple falling from a tree and the moon in orbit. So what Newton realized is the moon is also falling. It's just that it's moving laterally, so it keeps falling, if you will, around the edge of the earth and keeps going. With that, he was able to formulate the law of gravity, that there exists a force that's proportional to the masses and inversely proportional to the square of the distance. Very simple equation. The laws of thermodynamics, the laws of energy required recognizing the conceptual equivalence of very different kinds of energy: potential energy, gravitational potential, chemical energy, elastic potential energy, and kinetic energy, energy of something in motion, and surprisingly, heat. Once this was realized, then you can have the great experiment of James Prescott Joule, where he took gravitational potential energy of weights, he converted it to the kinetic energy of a spinning paddle wheel, and you can measure the heat generated in the water. That's the first law of thermodynamics. And the second law, that heat's form of energy and that it always will spontaneously move from the warmer to the cooler body. And finally, the laws of electricity and magnetism. These could not have been discovered until you recognize that electricity and magnetism are 2 aspects of the same force. When Hans Oersted did his experiment passing a current through a loop of wire, creating a magnetic field, he showed this very soon thereafter. People invented the electric motor, the electric generator, and also discovered, quite surprisingly, that light is another phenomenon related to this, electromagnetic radiation traveling at the speed of light. Okay, so here are the 4 laws. Is that enough? Is that enough to describe our natural world? And I'd say no, because there's something missing here. And that has to do with this wonder of the natural world, that are evolving systems from stars to minerals to planets to life. These varied systems are conceptually equivalent in the following senses. They all are systems that have the potential to adopt vast numbers of configurations. Whether it's atoms or molecules or cells, they can rearrange themselves in many, many, many different ways. And there are processes that make these configurations in nature. And finally, and this is key, you select for function. You select the configurations that work in the context of what you're talking about. Let me go through a few examples of this. I think this is a lot of fun. You start with a Big Bang. There are 3 different chemical elements: hydrogen, helium, lithium, primarily. You form the first stars. The first stars make a few more elements. The next generation of stars building on this makes a few more elements. Stars explode. The next generation of stars makes almost 100 different chemical elements and almost 2,000 isotopes. This is nucleosynthesis. It's a process of evolution. We've seen mineral evolution going from 20 minerals to almost 6,000 over 4.5 billion years. What I didn't show you is you can show that this complexifies. There's the curve of the increasing number. Here's the stages from 1 to 10 of those mineral evolution. But the chemical complexity measured in bits increases, and the structural complexity measured in bits also increases through time. Of course, the big example is Charles Darwin and evolution by natural selection. What Darwin said is individuals in a population display variations in traits. There's lots of different configurations. He said more individuals are born than can survive. That is, there's a way through sexual reproduction of generating lots of new configurations. And then you have selection. Selection for whatever function allows the offspring to survive. And of course, Darwin talked about the beaks of finches, lots and lots of different configurations here. You have a large configuration space. You select the beak that works for your diet, whether it's nuts or insects or berries or whatever. I want to go into one example in a little more detail because I think it's really important to see how powerful selection can be. I'm going to talk about the evolution of the eye. And many people criticize Darwin saying, what's the use of half an eye? Well, Darwin said, and 30 years ago, researchers used a computer algorithm to demonstrate that half an eye can be very, very useful. Start with a situation where you have a clear layer of transparent cells. This is on the back of a worm, a sightless insect, or some other animal that doesn't have an eye, but would benefit from being able to see a shadow passing overhead. So if you have a white layer of transparent cells, a gray layer of light-sensitive cells, and then a black layer, which is the substrate underneath. And the rule here is very simple. You randomly vary 3 parameters of this situation. One is the curvature. You can make it bulge outward, you can make it bulge inward. The second is the aperture distance, the distance between there. And the third is the index of refraction, that is how light bends in that transparent layer. And you just run the computer program, and anytime you increase the acuity, the visual acuity, that's spatial resolution, you take that change. You can say, just even being able to see a shadow move a little bit better gives you an advantage over an individual that doesn't have that. And so 176 steps, you start with a flat surface, you get a concave pit. And with a concave pit, you can see which direction a shadow is coming from. You run this a few more 100 times, almost 1,000 steps, and eventually you end up with a circular cross-section, which is much better at determining direction. In fact, this is what the eye of the limpet looks like. But remember, you can also change the index of refraction. And so in the next several hundred steps, you start increasing the index of refraction and building a lens. This is all through selection now. And a few hundred more steps, you start closing in that aperture. And in fewer than 2,000 steps, and you can repeat this over and over and over again with random steps, and you always end up with the perfectly formed, for this particular configuration. You cannot make a better eye under these circumstances. It's deterministic. You always arrive here because selection for function works and drives evolution. Another example I love is trumpets. 400 years ago. And so this is material culture evolution. Trumpets were long tubes that were rather awkward and played about 10 different notes. People wanted to be able to play more notes, so they started putting holes in the side of the brass instruments like a saxophone. It didn't sound very good, but at least you got more notes. And then finally, after the steam engine was invented, you got airtight valves. You can make a modern trumpet and play all the notes. That's evolution of material culture. And it occurs in popular culture too. And I got to share with you some pictures of Broadway musicals. Here's the variety show from the 1920s. This is Broadway. Well, things progressed, if you will. Rodgers and Hammerstein, Carousel, 1945, where they introduced not only quite a different kind of music, but also ballet in the dancing. Cole Porter's great Kiss Me Kate introduced jazz dancing, and a different kind of music. That was the year of my birth, believe it or not. I should give that away, but and then what some of us might think of as a punctuation event. Leonard Bernstein, lyrics by Stephen Sondheim, the great choreography of Jerome Robbins, mixing jazz and ballet, and incredible. Well, you can fill in the next 60 years your favorite Broadway musicals. Selection, by the way, is who buys tickets. Simple as that. So look at each of these systems have the potential to adopt vast numbers of different configurations. There exist mechanisms to generate new configurations, and there's selection. Selection. So what do we mean by function? And Mike Wong has suggested that there's three main directions. One is just static persistence. If something just sits there and survives, it survives. There's dynamic persistence, like the sun and other stars, which last for billions of years in some cases, very dynamic. But there's also novelty generation. When you generate novelty, you take things in new directions. You develop an eye, you develop a wing, you develop a fin for seeing or flying or swimming. And so you enter new configuration space and you can try new sampling of a larger configuration possibility. But we also have to ask, what's the metric? Forces, motions, electric charge, mass, they all have units. What's the unit for evolution? And we would suggest that the metric is information and the unit is bits. But not just any kind of information, a specific kind that was introduced by Jack Szostak almost 20 years ago called functional information. And then Jack and I developed this further in 2007 in a paper in the Proceedings of the National Academy of Sciences. What we recognized was you have a large configuration space, but if you want to have a function, for example, an enzyme that triggers a reaction, the more and more efficient it is, the fewer possible configurations are going to let you make that particular function. If you're going to evolve an eye, there are many, many different possible configurations, but only a few are an ideal eye. And so this is the sort of graphical representation. And here's a very, very simple equation, which just basically says the information in bits, the functional information, is the negative log to the base 2 of the fraction of all possible configurations that achieves that degree of function. So anyway, that's a lot of words, but It's just an idea that you can quantify this, at least conceptually. So what's a missing law? What do we say? It's that it has to describe a universal trend in the macroscopic world, evolving systems. It has to be fully consistent with all the other laws of nature, and all of these systems certainly are. It does not follow inevitably from the other laws of nature. I don't think it does. I think this is something new. And so here's our proposal for the missing law. The functional information of a system will increase, that is, the system will evolve if many different configurations of the system undergo selection for one or more functions. We suggest this is a law of increasing functional information, maybe a key step in describing what's special about evolving systems. But I worry. Why hasn't anybody said this before? Nothing I've said tonight is at all mysterious or strange. Evolving systems are around us all the time, and we see them. This idea of functional information is pretty straightforward. It's pretty simple, just the number of bits of information in a system. So why hasn't anyone done it before? Maybe we're wrong. Maybe this does just follow from the laws of thermodynamics. Maybe these different evolving systems are not conceptually equivalent. Maybe there's something fundamentally different about them. Maybe there's something else we've missed. And so we're thinking really, really hard about that. I think a second reason is because Darwin was just so darn convincing. Darwin described natural selection. He described common descent. And it's such a paradigm. It's the way, when you think of evolution, you think this. And clearly minerals don't do that. And so if Darwin's natural selection is equal to evolution writ large, then there is no natural law here. But we would argue, as opposed to this, that Darwin is just one very important special case of a much, much larger natural phenomenon. So finally, I think this really lies at the heart of why it hasn't been articulated before. Because what we're describing when you talk about selecting for function is selecting winners and losers. Some configurations have more value than others. More value as an eye, more value as a fin, more value as a wing. And by extension, there's this hint of something about progress, of purpose, maybe even meaning in nature, which is just, that's for philosophers, that's not for scientists to tread. Think about these systems though. We're selecting for static persistence or dynamic persistence or novelty, which generates new configuration space. You start with 3 elements, but after stars go through multiple generations, you end up with almost 100 stable elements. You start with 20 minerals, but after 4.5 billion years of Earth evolution, you end up with almost 6,000 minerals. You start with a blasted black planet covered with volcanoes. You end up with this. You start with a single cell. You end up with birds and butterflies. And the human brain that can create music and dance and can think about missing laws. Is that progress? Are we bumping up against ideas of meaning and purpose in the cosmos? I don't know, but I do know that scientists do have this fear of talking about winners and losers, about that kind of function which is more valuable than the other. And yet I suspect that that is how nature works. Thank you.
Thanks, Bob, very much for an absolutely fascinating talk. We have a lot of questions and they're streaming in. I'm going to start with a very simple one for you. And that is, it's also our most popular question. Do you have a favorite mineral? And you can't choose Hazenite is one restriction.
No, I wouldn't choose Hazenite. Hazenite is microbial poop. Hazenite happens, but no, I really love pyrite because it has so many, first of all, it's beautiful. It's also common and it has so many different ways that it forms. It basically shows us the richness of the natural world in ways it can make minerals out of our planet. It's just, so I love pyrite. Fool's gold.
Are they being selected for? No, I won't go there. Is there a certain mineral on Earth that if found on another planet would suggest that planet was on its way to developing life?
So is there a specific mineral that suggests biology, a biosignature? We don't think so. What we think is that there may be distributions of minerals, perhaps revealed in the structure of the network diagrams I was showing you early. And the structure of Earth's network is different from the structure of other networks. Mike Wong has shown you in his previous lecture that the structure of the atmospheric network on Earth appears to be different from the atmospheric networks on other worlds. And so we think that this may be the key. So it has to do with a much larger scale picture of mineralogy on a planet.
Do you or fellow scientists predict that human behavior and artificial minerals from smelting, mining, etc., will lead to an 11th stage of mineral evolution?
I love this question. We have actually written a paper on the 11th stage of mineral evolution, which I didn't talk about tonight, but that's the anthropogenic minerals. And it's very important in the philosophy of our time, because if in fact humans are making a geological marker layer with laser crystals, with silicon wafers, with bricks and mortar and other sorts of synthetic materials, and if that marker layer therefore forms a geological time period, the implication is humans are having a huge impact on our globe. Some people don't want to say that. Some people are desperate to say that. And so the debate goes on. So watch the news to see if the Anthropocene epoch is approved by the International Geological Committee that decides on these things.
Okay, I'm gonna move ahead a little. There's so many questions here to choose from. This is a tricky one. This question I have as well. How does entropy relate to your proposed new law?
Oh. Can I ask Mike? Can I ask Anna? Can I ask somebody else to ask? Yes, I think it's a red herring. I don't think that entropy is, first of all, the way these systems behave through selection. It certainly has to be consistent with the second law of thermodynamics, which is what is being asked. I just don't see how you can derive this from the second law of thermodynamics. I'm sorry. I mean, I've been around for a bunch of years. I've been thinking about this, and no one has yet convinced me that this is the product of the second law of thermodynamics. But I may be wrong.
Wait, did you say, I'm so sorry, that has to be consistent with the?
It has to be consistent with the other laws. The other laws of nature are so well established that whatever we come up with has to not only be consistent with it, but also not follow logically directly from those other laws, those other 10 statements: motion, gravity, electromagnetism, energy. So that's the question. Is there something more? How can you deny it? I mean, it just seems to me but we could be fooling ourselves.
So, Bob, how would you describe mechanisms of reproduction and mutation among minerals? Both processes seem plausible, but as a biologist, I wonder how they might work.
We have to be very careful in taking the analogy between minerals and biology too far. They're both evolving systems, so there are some similarities, conceptual equivalences, but there are many things that are not equivalent. And common descent doesn't happen in minerals. An evolution of a quartz crystal into some other kind of crystal doesn't happen unless you subject it to very high temperatures and pressures. And so we really have to be careful. We have thought about talking about the mineral genome, but all we mean by that is all the different information-rich properties of a given specimen, not the fact that it's got genetic information that it passes to its offspring.
Gravitational fields of other planetary bodies vary widely from that on Earth. what are the effects of varying gravity on mineral formation? I like this one.
That's cool.
And observed and expected mineral species, right?
It would certainly have a huge effect if you're talking about deep interiors where the pressures and temperature regimes would be different. It would be more important to know what the atmosphere and the hydrosphere look like. Those are what the big influences are, because you're transporting atoms at a local level. Minerals grow in a very local level from seeds and so forth. So gravity doesn't really have a whole lot of influence on the growth of this crystal, but the fluid environment and the atmosphere will have a huge environment, and of course, biology as well.
Okay, I'm going to take two more questions. This one related a little bit to Mike Wong's Science of Star Trek. What kind of mineralogy would result on a planet with silicon-based life?
Well,
Good luck
okay.
with that one.
And once again, I would defer to Mike's expertise, but I think he showed pretty clearly in his talk that it's unlikely that we'd have silicon-based life simply because the chemical bonding doesn't give the kind of plasticity that you get with carbon. But if you were going to have, it would have to be very high temperature, because otherwise it would just be frozen. You know, it would just be like carbon-based life at minus 50 Celsius. It would just freeze, and that would be it. So I guess it would have to be at 800 to 1,000 degrees Celsius, and maybe you could have some interesting chemistry going on.
Right. I had another one here, which was very philosophical, but one of the problems with this particular thing is that as the questions come on, they move away from my line of sight. Okay, how about one more question here? Here it is. Bit of philosophy. What's the most profound personal insight that you've acquired from your 15-year survey of all known minerals?
I find it astonishing how many different ways planets have of rearranging atoms. Planets are incredible engines of diversity. They generate through fluid rock interactions, through atmospheric effects, through impacts and lightning, through the deep interior and plate tectonics. You have so many different regimes of pressure, temperature, composition, time that leads to this incredible richness. You think about Earth and compare it to our dry and lifeless moon. There's something profoundly beautiful about the way our planet works as a dynamic system.
I couldn't agree more. Well, very well said. And let's thank Bob one more time.